Understanding the GPU memory hierarchy is essential for optimizing performance. This section explores where different memory levels sit in the architecture and how they relate to each other. This view isolates a single streaming multiprocessor to show which memories are contained within it and how they fit into the GPU. GPU memory is organized in layers, trading speed for capacity. Faster, smaller memories are closer to the SM, while slower, larger memories are farther away. CPU system memory is located off-chip and is accessed over interconnects such as PCIe. It has higher latency and limited bandwidth compared to on-device memory. HBM3 memory stacks are located off the GPU cores but on the same package. Each stack has its own controller and the hardware routes requests automatically. These stacks provide large, high-bandwidth storage for global data. L2 cache is shared across all SMs via the GPU's chip-wide interconnect. It sits between SMs and global memory to allow data reuse and reduce traffic to HBM stacks. L1 cache and shared memory reside in each SM. L1 provides fast caching, while shared memory is explicitly managed per SM and only accessible to threads running on that SM. Registers are located inside each SM and provide the fastest storage for threads. Each partition within an SM owns its own register file. Registers are allocated per thread at compile time and remain reserved for the kernel duration. Now that we have an overview of all memory layers, let's have a final overlook. CPU system memory resides off-chip and is accessed via PCIe or other interconnects. Bandwidth is limited and latency is high. Transfers can be explicit or managed by unified, page-locked memory. The interconnect bandwidth is often the limiting factor. HBM3 memory consists of multiple independent stacks, each with its own memory controller. Requests are routed automatically by hardware to the correct stack, allowing many parallel accesses. Coalesced memory accesses are critical for performance, as explained in the linked video. L2 cache is shared across all SMS via the chip-wide interconnect. Data fetched by one SM can be reused by others. Hit rates depend on access patterns, and modern GPUs support hints for persistent caching of frequently used data. Shared memory in each SM is divided into banks, and access is limited to threads on that SM. Bank conflicts can significantly impact performance. Access patterns determine latency, and these effects are explained in the linked bank conflict video. Registers are divided into multiple partitions inside each SM, with each partition owning its own register file. At compile time, the compiler assigns a fixed set of registers to every thread, and these registers remain reserved for the entire kernel. Warp switches simply select a different register set. There is no saving, copying, or restoring. Efficient kernels use only what they need and reuse registers carefully to stay fast. Efficient GPU code relies on careful data locality. Keep frequently used data in registers, share intermediate results through shared memory, and structure algorithms to maximize L2 cache reuse. Batch global memory transfers and overlap them with computation to reduce latency. Understanding the GPU memory hierarchy allows you to optimize performance effectively.